Today, we're diving into the story of a powerful computational model that was built to understand how we learn and the single critical blind spot that nearly brought the whole thing down. I mean, think about it. It's one of the biggest questions in cognitive science. We build these incredibly complex models to simulate the human mind, but can a bunch of equations ever really capture the messy, unpredictable, and amazing process of how we learn? Okay, so to really get what's going on here, we first need to talk about the basics. We need to look at the actual shape of learning itself. Just think about the last time you learned a new skill, right? Maybe it was an instrument or a new language, or even just a video game. Sometimes you improve really, really fast at the beginning, and then you hit a wall. Other times, it's this slow, frustrating grind before everything finally clicks into place. Well, that shape of your progress, that's what scientists are absolutely fascinated by. This visual map of your progress, this line on a graph, that's what we call a learning curve. And the most important part is the bend in that line. It's curvature. That's the secret sauce. It's a number that tells us the rate of your learning. Is it fast? Is it slow? Or is it somewhere in between? So to try and predict these very curves, scientists back in the 1990s developed a really ambitious computational model. And that model, well, it's at the very center of our story today. It's called the exemplar-based random walk model. Yeah, it's a mouthful. So we'll just call the EBRW model. Its whole job is to act like a mini brain on a computer, trying to simulate how we get faster and better at tasks the more we practice them. Now, the EBRW model didn't just appear out of thin air. It was actually built in 1997 as an extension of an even earlier model. So you can see it was a pretty big step forward in this quest to mathematically describe how we learn. So, how's it supposed to work? Well, deep down in its code, the model uses a very specific mathematical formula, a power function, to predict how our response times should get shorter and shorter as we practice. It's trying to chart that exact learning journey. But this is where the trouble starts. Because while this model was beautiful and elegant in theory, it ran smack into a huge problem when it was compared to actual real-life human beings. You know, what happens when your beautiful, clean mathematical prediction crashes right into the messy reality of how people actually learn? This is the ultimate test for any cognitive model, and for the EBRW, the whole conflict came down to just one single number. 1. That's it. The entire model, with all of its complex math, was built on a foundation that always inevitably led back to this one single number. And that number? That was its blind spot. And here it is, the model's fatal flaw. Because of the way its internal math was structured, the EBRW could only ever generate one type of learning curve, one with a curvature value of exactly 1, a perfect, rigid, one-size-fits-all prediction. And you can see the problem right here. The model's world is over on the left, one single, unchanging curve. But on the right, that's the real world. That's us. We learn at all different rates, creating this whole family of different curves. The model was stuck predicting a value that was, and I'm quoting here, rarely observed in analyses of empirical data. It was basically wrong almost all of the time. So let's just recap the conflict, right? The model predicted one and only one learning rate. That rate almost never actually showed up in real-world data. And even when scientists tried to patch the model or tweak it, that same fundamental limitation was still there. The model was completely stuck. But this is where the story gets really cool. The researchers didn't just give up and throw the model away. Instead, they came up with a solution that was surprisingly elegant. See, the idea wasn't to start from scratch. It was to pinpoint the one faulty component in the mathematical engine and perform a kind of surgical swap. So here's the fix. The original model used a mathematical rule called an exponential distribution. The easiest way to think about it is like having a ruler that can only measure in whole inches. It's precise, but it's not flexible at all. That was the source of the problem. The solution? Swap it out for something called a Weibull distribution, which is like a much, much more flexible ruler that can account for all the little measurements in between. And with that one change, just like that, everything opened up. The new, upgraded model was no longer locked into predicting that single lonely curve. It could now accurately account for the huge variety of learning rates we actually see in real people. The blind spot was gone. So why have we spent all this time geeking out over one number in one specific cognitive model? because this whole story actually reveals something fundamental about how science works.
As the researchers themselves put it, learning curves are a powerful form of evidence. Being able to predict them accurately isn't just a neat party trick for a model. It's one of the toughest and most important tests it could ever face.
Think about it. If your model can't replicate this basic pattern of human improvement, then you know there's a serious flaw somewhere in its design. Getting the shape of learning right is the benchmark for success. It tells you whether you're really on the right track to understanding the mind. So what's the big takeaway here? Well, first, that these computational models are absolutely essential tools. Second, they're only useful if we are constantly and ruthlessly testing them against reality. And maybe most importantly, discovering a flaw isn't a failure, it's an opportunity. That one broken number pointed the way to a much, much better model. And that leaves us with this one final fascinating question. The story of the EBRW model shows how one tiny mathematical detail can have these massive consequences. It really makes you wonder, in the vast, complex code of the human brain, what other critical details are we still completely overlooking?